Okay. Uh, mm, ठीक है ना? मैं तो मिलूँगा. So today's plan, uh, we have two back-to-back lectures now. We'll have a break in between. Uh, so yesterday I shared you this article by Delgado, okay, which is on the Lagrange short fit method. So this paper has in the first part discussed general integrals and singular integrals, which we discussed yesterday. And in the second part is where he has this Lagrange short fit method. This method is to find a complete integral for a nonlinear PDE, which is x, y, u, ux, uy equal to 0, or one also writes f of x, y, z, p, q equal to 0. Both are standard notations, though I would actually prefer this because an equation should have the unknown part, right? Here in the second equation, it is f of x, y, z, p, q equal to 0. So it's not clear what is known, what is unknown, right? And also often people differentiate this f with the p. Okay, if you think p is ux, a solution and its partial derivative, what do you mean by differentiation, right? So usually the correct setup to write this, in some of the old books also they write this, which is a good thing. They are going to describe what your function f, you start with just a function of 5 variables. The variables are called x, y, z, p, q. Okay, just a function from somewhere in 5 dimensions to real length. Just a function, nothing to do with PDE. Then what they're saying, my PDE is this. What is that? Find a function u such that f of x, y, u of x, y, ux of x, y, uy of x, y equal to 0. This in short is this x, y, u, ux, uy equal to 0. Okay? Okay, this is the equation. Often you will see notations like this: fp, fq, fz, fx, etc. It means nothing but the derivative of this function that we have introduced here. This function. So if I say fq, it means I am differentiating this function with the fifth variable. Okay. You will also see in the literature people writing dou f by dou uy. Okay, what I would write dou f by dou q. Okay. So all these notations are okay as long as we don't get confused, right? But first time learner, it is matter for confusion actually. Including when you read this book, without this kind of clarity, there is a problem. So clarity is important. Once you understand, you can write anything you want. Because you know what you are writing, what you are saying. That's important. Okay, now, okay, so what is the plan here? So the idea is this one, complete integral for this. This is called just Chadwick method or Lagrange Chadwick method as this paper calls. And then we move on to another method which is Jacobi method. It's not that it's another method for solving same equation. No, it's solving some other equation. That is f of x, y, z, u, ux, uy, uz equal to 0. Now it's clear. They are solving partial differential equation first order where you have 3 independent variables. Okay? So we'll spend most of the time on chart-fit methods, which is solving equation in this one in 2 independent variables. And then we see the analogy how it's going from 2 to 3 variables. We can compare side by side. Because an extra variable is coming, they need to add something extra. After that, everything is same. Method is exactly same. Perhaps Jacobi did independently those days, but now we see everything in a unified manner. There is nothing different, though it's written as a separate chapter in the book. And then I will write one more, 4 variables. There is no end to this. Okay. Important thing is the method should work, right? Always when we describe method, we say it works only for those equations for which it works. This is how it is, because there is going to be conditions anyway. So that is how. And in between we will discuss this compatible system of PDEs. I mean, some history attached to this. Okay. Origin, of course, lying in Sweden, but I mean that's the most popular book, so it's written there. And from there, how things are transformed and how Professor Amarnath's book clarifies it. And why I need to study this as a separate topic, right? What follows study of this is the chart-fit methods. So its utility is in designing this chart-fit method to solve first order PDE in 2 independent variables. Okay? In between they see something which is plays a role, so call it a separate topic so that we remember, that's all. In fact, if you see Delgado's, he doesn't use this word compatible, but whatever is needed he is doing inside. But because this has become a topic on its own in various places, so we will discuss this explicitly. And then we see how it appears in this method. Okay. Now, just a few recall or clarification. On definition of complete integral. It's the equivalent version I am going to write, so that you will see one in one book and then one book, we have no problem. It is one and the same thing. I want to emphasize that. And first let us start with what we did yesterday, which is actually from Courant Hilbert. So what did we say? Somebody is a complete integral for what? That we have to mention. It's not for all equations. It's for this f of x, y, u, ux, uy equal to 0. Right? For this equation. What is that? It should be a function. We write z is equal to phi of x, y, a, b. Right? Of course, smooth. Such that first thing is, for every fixed parameter value, phi of xy ab should be a solution to the PDE. When I say PDE, this is the PDE. Okay? Second one was a rank condition. Rank of a certain matrix is equal to 2. And that was phi a, phi xa, phi ya, phi b, is 2. Okay? To even think of this second order partial derivatives, we don't want any problems depending on the order in which you find the derivative, because we do know that order of differentiation is not interchangeable. Interchangeable only when things are nice. So let's assume things are nice. So that means I have here what kind of derivatives? X and a, y and a, x and b, y and b. Right? One medicine for everything. I assume this phi is a C2 function. on its domain. Don't mention what the domain is. Okay? So C2 function we have to add. Now, what is in Delgado? Because I have given this thing so that you should be aware that both are not different things. So Delgado doesn't write z equal to 5xyab. For him it is just a function. I am using capital 5, okay? Don't compare these two with the notation. So he says this is f of x, y, z, a, b, okay? And phi, obviously there will be some derivatives, so C2 function wherever it is defined. Okay, with what property? First property. For every parameter AB, parameter is still AB, fixed. In the case of Courant-Hilbert thing, we directly said phi of x, y, AB should be a solution. But now I don't have anything here, right? I don't have z solved in terms of x, y. So what they'll say, this fixed, the equation capital phi x, y, z, a, b equal to 0 has something sitting inside which is a solution, right? Has one or more also okay. Okay? Imagine x square plus y square plus z square equal to 1 or something. So you can have two values. So one or more solutions of the PDE. Okay? That means there is a function, at least one function u of xy such that capital phi of x comma y comma u of xy comma a comma b equal to 0. So here I could directly say, because I have assumed like this, u of xy equal to phi of xy, right? Here it appears as a graph of the function in the Courant-Hilbert case. In the other case it does not come. But we have reconciled, right? So what essentially we are saying is that you should be able to solve for z in terms of xy, a, b from here, which is implicit function theorem, right? So under some conditions you can do. Let's not worry about what are the conditions. We can always write down the conditions, but most probably they are all sufficient conditions for solving. But at least we know that I know some theorem, implicit function theorem. It tells me that I can solve for z in terms of the rest of the things. That is possible if dou capital phi by dou z is not 0. That is the main condition in implicit function theorem at some point. Then around that point you can find solutions. And of course, if you are able to apply implicit function theorem, you will have a unique solution also in a neighborhood of that point. So let me not get into implicit function theorem, but I am just giving you that we have an insurance. Okay, when it needs to apply, it will apply. You don't have to worry. Now, second thing is about the rank. Here, phi a, phi x a, phi y a, phi b, phi x b, phi a b is there. That z is not coming anywhere because z has kind of come on the side, right? Now, if z is included, like here, what should be the condition? We will see very easily. It's also going to be phi a, phi x a, phi x b, phi b, phi x b. Yeah, this is phi. I'm not doing some theta inside. Phi b. You simply had to add one extra. That is phi xz, I think. Let me just see. Or za. No, then I have made a mistake. Yeah, see, you're not telling me. This is phi xa, phi ya. I'm just imitating what is on the LHS, no? Phi b, phi xb, phi y. That's right. So now phi za, phi zb. So rank of this matrix is 2. Okay. Okay, now compare this. Courant-Hilbert guy is also contained in our Delgado thing, with capital phi being small phi minus z, right? And if it's small phi minus z, this particular column is 0, because the moment you differentiate with respect to z is 1, then it does not depend on A or B. So this is 0, 0. Okay, so rank of this matrix, which on RHS is 2, if and only if the rank of the matrix on the left hand side is 2. So both are one and the same. Okay, this is important for us to Understand? Because now if you open this book, you should not feel that this is something else. That's why I have done this. Now in Delgado there are two theorems, theorem 1 and theorem 2. It is simply nothing but the envelopes notes which I have assigned to you. If you have a family of solutions, if you take envelope, that is also solution. Depending on how you take envelope, whether you take both the variables together or just one variable, but you have two constants there, so other one has to be written as a function of the first one. We did this yesterday, and then they are actually justifying that it's a solution. So I will not get into that. So that's the theorem 1 and 2 written in full glory with all details. Exactly how you should apply implicit function theorem, inverse function theorem and all that. So this is for you to read when you already study some inverse implicit function theorems. Is that okay? So I am not going to do that. I thought of doing, but then I will not do it. So this comparison, once we have, everything is fine. We'll come back to Delgado when we do chapter. Now I am going to move to TAM, TM1R, and do compatible systems. So I was thinking, what are these compatible systems before seeing the definition? Okay. Then I came up with an idea. I will explain you that. So only two, okay. You can think of many, but here it's explained two. Most probably what is needed in Jacobi method will be three. Okay. So once you know how to do two and how to generalize to three, you know how to do it for any number of variables. So here it's actually two equations are discussed. Compatible systems of first order PDEs. So we have to start with two first order PDEs. So f of x, y, z, p, q equal to 0. You can think of u, ux, uy also there. And another one is g of x, y, z, p, q equal to 0. So the equations, this and this, are compatible. Domains and all, let's not worry, but he has written, so I will just write compatible. They may be compatible, the definition holds. So in some places, may not hold in some other places. So we will write compatible and a domain D. This you can ignore from now onwards. If, what are the conditions? What do you think will be the definition of compatibility? Do we have any English experts here? So I will take their opinion first. Oh, I am very happy. At least nobody is saying they're expert in English. Okay, now open to people like us who don't know much English. What do you think is the answer? When do you want to say these two are compatible? Yeah, I have to take names. Please respond.
I had a joke in mind. It said compatible with husband and wife.
Yeah. Use that logic and tell me this. No, we started, so it can't stop there. Yeah, good. Huh? Similar. These are not matrices. Yes. No, he has given very objective answer. He is telling they should have same solution, set of same solutions. Very clear. That means somebody solves f equal to 0 if and only he solves g equal to 0. But according to English, husband is not equal to wife. He says only compatibility. So I don't know. We don't know what compatibility is, right? I used to think exactly like what's our Madam, you were saying something.
They have similar properties.
Similar properties,
On the
solutions.
on the-
Solution should
on
have
the-
similar properties.
Solutions are similar.
Which kind of looks like having same solutions in some sense. It's disguised form. Nilesh, any improvisation? Yeah, Nilesh is correct actually. One thing is, it's not in mathematics, that's all. See, if you are asking two equations to have same solutions, it's okay. Then why you want to say compatible? No, they are one the same. Then I thought, no, maybe there is some change of variables involved. But notice xy are same in both the equations. Some change of variables is there, f may be in domain here, and u guy is there. So he is sitting in this guy's there. He has transformed up to that place. That's what I thought. But then xy is same, so I didn't know. So I was searching the meaning and then not getting anything. So then I spoke to some of my friends. Then the guy who already knows this material, he gave me the funda similar to what you said. See, compatibility means they have something in common, that's all. Okay? The problem is, the first thing I did is, I didn't look at this book, I didn't know. Madam sent me these topics, I thought it is from Sneddon. I opened Sneddon. He's saying they should have exactly every solution of f equal to 0 is a solution of g equal to 0. And nothing to choose from f and g. Therefore, every solution of g equal to 0 is also a solution of f equal to 0. This is a natural thing. This is what Sneddon has written down long back. But that is not the case, okay? So, we were going to define. You will see the definition. Definition also will not reveal anything. Let's see. Domain if, first condition, j is equal to, by now you should get used to this kind of notation. This is quite standard I am seeing now. This just means that you have fg, this is the derivative with respect to only pq. Forget about x, y, z. Okay? If you want, in the implicit function theorem, we will see that. We will have many variables, but we are interested in derivative with respect to some variables. So this is that. So this is nothing but dou f by dou p, dou f by dou q, first row, dou g by dou p, dou g by dou q in the second row. Now this is how I have learned to write, so I write like this. One can also write the transpose of this. Okay, you have two functions, f and g. Their functions are variables pq. I already set aside x, y, z. They are fixed. So I have f and g treated now as functions of pq for every fixed x, y, z. I am asking about its determinant. I mean its derivative, first derivative. So f and g, take the first function, differentiate with respect to both the variables, grad f with p and q, put it in the first row. Take the second one. This is the one. Okay. Okay. So what they are saying is, but here it is. This means actually the determinant of this matrix, Jacobian. That's why the indicative j here. That should be non-zero on D. Okay. You may be taking derivative only with respect to p and q, but at every point, this is a function of x, y, z, p, q. This should be not zero in your domain D. Okay. Actually, I already gave some kind of clue here. I immediately connected this to implicit function theorem. So they are actually interested in solving for p and q using this f equal to 0 and g equal to 0. Okay. So at this point, they are not taking any PDEs here. Just a function of 5 variables equal to 0, another function of 5 variables equal to 0. First condition is that the Jacobian with respect to p and q of f and g is not 0 in the domain D. Therefore, by implicit function theorem, now if you say implicit function theorem, it only says locally you can solve. But here I told you, we are not claiming to do something big. We are interested in finding a solutions to this PDE. However small domain it is defined, I don't care. First I want to have a solution. With that in mind, I am going to assume that, I am solving for P and Q from this relation throughout my domain D. So that's the second assumption. P is equal to some function phi of x, y, z. These are the other variables in the problem, right? X, y, z. PQ I am solving in terms of x, y, z. That's how you should see implicit function theory. And Q is equal to psi of xyz. I am able to solve this. See, the way they write is and P is equal to this, Q is equal to this. They are coming from actually this solutions, that means satisfying f of x, y, z, p phi of x, y, z, psi of x, y, z equal to 0, and g of same argument equal to 0. That means I am saying that phi and psi solve this. I have solved for PQ in terms of x, y, z. Those functions I am calling phi and psi. Okay? Not only this, they want this to happen. This we know that by implicit function theorem, in view of 1, it is possible only locally, but OK is possible everywhere. Assume that kind of thing. And then what happens? P equal to this, satisfying this, it's not full stop, continuation. Render or make this the Pfaffian, so I will write Pfaffian. Which Pfaffian? dz is equal to phi of xyz dx psi of xyz dy integrable. Okay? Then I will say these two guys are compatible. Okay? You see, this definition does not feature anything. First two things it talks about implicit function theorem. The real PDE part is coming a third one. They are saying this Pfaffian is integrable. Okay? But where is this compatibility? Right? Okay, suppose it is integrable. Okay? There will be solutions to this. What will those solutions do? So, suppose you have a solution, let's call this as a Pfaff, P. Okay? So, just remark, P solvable. What does it mean? There is a function u of xyz, right? With what property? Dou u by dou x is equal to phi of x, y, u of xy, right? And dou u by dou y is equal to psi of x, y, u of xy. Correct? Done. But what is phi? It is p, no? What is p? It is satisfying some equation. So therefore, that will give us what? F of x, y, I put u of xy, I put phi of x, y, u, xy, psi of x, y, u, xy is 0. And so is g of the same thing equal to 0. Okay? But this is precisely ux, this is precisely uy. That means the solution of this Pfaffian equation is actually a solution of f equal to 0 as well as g equal to 0. That means they have a common solution. Right? So that is the consequence of all these assumptions. So therefore, is that f equal to 0, g equal to 0 have a common solution. What is that solution? Which is solution of Pfaffian equation. Right? Now question is, how many solutions this Pfaffian equation has? Because I am assuming it is integrable, right? If once it is integrable, how many solutions are there? One parameter family. Right? Pfaffian equations, if they have solutions, it is one parameter family of solutions. In fact, one parameter family of solutions. In fact, we can write common solutions. So this is actually should have been the definition. But why they have inserted this Jacobian non-zero and all that? Because they have a theorem in that hypothesis is needed. Okay. Now the question is, we have defined, fine. You have f equal to 0, g equal to 0 is compatible, some conditions are there. Now tell me, by looking at fg, can I say they are compatible? Is there a condition which says is compatible? Of course, it has something to do with the integrability of this Pfaffian. For that we have conditions, x dot curl x equal to 0. Okay? So now what is x? Phi psi minus 1. That is x here in the Pfaffian. Right? Coefficient of dx is phi, coefficient dy is psi, coefficient dz is, when you transfer the other side, minus 1. Phi psi minus 1 is your x. But you don't know phi and psi. What you know about phi and psi is that they are common solution. I mean, they are obtained by solving for p and q using the two equations. So that's how it is linked to the equation. So then we will derive a condition for the compatibility of two equations, f equal to 0 and g equal to 0. If and only if condition. So that's why those conditions are put. But essential message is that if two equations are compatible, they have one parameter family of solutions in common. Okay? And what is the idea of using this in getting a complete integral for a nonlinear equation? You have a nonlinear equation given. Okay? And what is a complete integral? It should be a two parameter family. How do you get it? Idea is, you have an equation, no? Find another equation g equal to 0, which is compatible with it. Then what do you gain? They have common compatible. That means all the conditions. We have assured, find such a g. So then what will happen? F equal to 0, you have found one parameter family of solutions. Because you found another g which is compatible with it, and as a consequence of this definition and this remark, they have a one parameter solutions in common. But you wanted complete integral, which is two parameter family. What is the natural idea? Find a compatible, you have f equal to 0, you can't do any chat in that. Now you find a new set of equations, the g, indexed by another parameter. That parameter will come along with it, because it has to be a solution to that. And being common, you get one more parameter. So you pick up two parameters that way. So this is the idea of Chadwick method, to find a complete integral for a first order nonlinear equation. Okay, we will come to that. We will finish some small discussion about this thing. So original definition, why the definition may look ugly like this also. See, many times when we prove something or solve some problem, the proof may not be the best possible proof. Right? We get something, we put in. It's like that 7 stones game. You don't want a proper shape or something. You just put, somehow it should be there, and you won the game. So like that, anytime when they realize that something needs to be done quickly, this is how it is done. Okay? It may not look good because now this is written some time back. But if you see its origin, it's not written this way. It's written that every solution of this is also solution of that. Then people found it is not correct. And he also has a characterization. The funny part is that it's not that Snedden does not know. He himself has some example which says this is not possible. He has it compatible, f equal to 0, g equal to 0. It satisfies that condition which he is writing. But there are solutions of f equal to 0 which are not solutions to g equal to 0. That example he has. So, shoot over here because he is writing such a big book. So, we can miss something. So, that was corrected by Professor Amarnath. In fact, he communicated to him a number of times. Perhaps the book was never revised, so he didn't include this. And in fact, I used to hear this when I was doing my MSc, that Snedden has mistakes, Snedden has mistakes, and so on. I didn't know which one it is. Then after joining in IIT, some student from Punjab for some reason he wants to solve some problems of Snedden. He used to solve and send it to me by email. Then I realized that there is some, not induction, but some such kind of mistake is there. Oh, I thought, oh, this is a mistake. Okay. It is there. So you be very careful when you are running Snedden. Now I don't recall, but definitely that mistake is there. Then I told him, boss, it's not like this, there is a gap here. It's actually a theorem proof. Then I came to know about this. Okay. In fact, he has written a note in the book, we will see that. So the standard problems in this is show that f equal to 0, g equal to 0 are compatible and find a one parameter family of common solutions. That's how all the problems are. So we will do one exercise. Okay. Before that, we need to have this theorem. No? Okay. So theorem. We already have this. dAz is equal to phi dx plus psi dy. That is integrable one statement. So if and only if so there is some nice thing. This is some bracket. This is called some bracket, Jacobi bracket or some bracket. So this there is a formula. Okay. Dou fg by dou xp plus p times dou fg by dou zp. Just have a look at the denominators. Plus, because numerator is always dou fg. Dou xp is over, no dou yq. Plus q times dou fg by dou zq. This guy must be 0. Okay. This is a condition that you can verify. Right? You are given f and g. Just compute all these quantities. Check that it is satisfied. Then you definitely know it is integrable. Therefore, you know f equal to 0 and g equal to 0 have common solutions. On the other hand, you have f equal to 0, so you want to find a g equal to 0, find such a function g, such that g equal to 0, so that they have common solutions. What all you have to do is, you know your f, so in the condition given here, substitute the values for f, then you will get a partial differential equation for g. You solve that. That's precisely what Chadwick method does. So these two are equivalent. This is not 1 implies to 2 implies 1. It is straightforward. One go it goes. Now, one is saying that one holds if and only if x dot curl x is 0, where x is equal to phi psi minus 1. Correct? Right. What is the first statement? It says a certain fraction is integrable, for which we already know this. This we already proved. X dot curl x must be 0. I think we are not proved, I stated maybe. Huh? No, that was x dot curl x equals 0 if and only mu x dot curl mu x is 0. So then that means we have proved this. Okay. It's okay if you have not proved. Okay. We know this. So x dot curl x is 0, where x is this. So now we expand on this. What is x dot curl x business here? We know phi psi minus 1. So we have to compute what is the curl of phi psi minus 1. So it is phi psi minus 1 dot product with curl of phi psi minus 1, which is actually minus psi x this may be typo. Where is phi? Phi psi into phi z. I'm just writing, just check whether that is correct. Yeah, this is correct. Check this. Now we just, so there is nothing is lost, right? Everything is if and only. One is true if and only x dot curl x is 0, which is nothing but this. Equivalent statements. So that is if and only if. Just expand and rewrite. Psi x plus phi psi z is equal to phi y plus psi phi z. Okay? Minus phi psi x is there somewhere. What? Something I missed.
Curl will be
Minus
psi
psi
z.
z. Okay. No, it's okay. Yeah. Minus psi z phi z. Okay, fine. So we have got this. Now we will show that this second part is there, no, a certain thing equal to 0, which we will write as some LHS equal to RHS. We actually prove that this is equal to 1, this equal to 1. So what we are going to show is psi x plus phi y z, this LHS is actually equal to, that j being non-zero will be used here, 1 by j will come somewhere. Dou f g by dou xp plus phi times dou fg by dou zp. Okay. Similarly, we will show this. So this is LHS. We will show RHS is equal to, by doing the same same computation is same. So dou fg by dou yq plus psi into dou fg by dou zq. Okay. So therefore this is all if and only if, and if you write everything in one go, j is not 0, you can cancel, then you will get the condition that is mentioned, the bracket of f comma g equal to 0. Okay. So we will just check LHS equal to this. We will check only one part. Psi x plus phi psi z is equal to 1 by j dou fg by dou xp plus phi dou fg by dou zp. We will check this part. So this is where we use phi and psi are actually coming from our equations, and those equations we need to differentiate. So what are the equations that we have for phi and psi? One is this, f of x, y, z, phi of x, y, z, right? This is what we have, no? Psi of x, y, z. Because we solved for p and q, no? So this equal to 0. We also have with a g. Same thing, equal to 0. Now we have the option of differentiating this with respect to any one of the variables. So we will differentiate with respect to x and get some equation. Then we will write what will we get when we differentiate with respect to y. Let's see. So let us differentiate with respect to x. Differentiate with respect to x. Okay. First I will do for the f part. So that is nothing but fx. I will not write the arguments because space is not enough. Fx. Fy there is no need, that's independent variable. Z is where u of xy is there. So we must do that. Fz. But are we treating that? No, we are not treating. So xyz are treated as independent variables here. We are not thinking that. See, that means I am not in the PDE now. Remember, this is just the usual algebraic transcendental equations. We just solve for P and Q in terms of x, y, z and substitute here. There is no PDE. This is multivariable and chain rule. So no need to differentiate with respect to z. If there was a u of xy, then that we could have done, but now we should not. So fx. Now next is I need to differentiate f with respect to the fourth variable. The fourth variable we call it fp. Done. And then phi we need to differentiate with respect to x. So that is dou phi by dou x. Similarly, last one, fq. Q is the denoting fifth variable, and dou psi by dou x equal to 0. Now differentiate with respect to z, you get fz plus fp dou phi by dou z plus fq dou psi by dou z. Right? Similarly, replace f with g, but for g you do with y and z. You will get some relations. What you are interested in, what? Remember that. Psi x plus phi yz is what you want. Okay? See how you can get. Psi x is here. So solve for psi x maybe. Okay? And then solve for psi z somewhere. So please go through the computation in Amarnath. Idea is to, I already explained, right? Get that bracket equal to 0 by showing that this LHS is this, RHS is this. And then now let us do this exercise. So show that the equation f is equal to p square plus q square minus 1 equal to 0. Are compatible, and find the one parameter family of common solutions. Yeah, thankfully this checking is much easier because first one does not have XYZ variables. Second one does not have Y variable. So please check. So checking this equal to 0 is exercise. That's a if and only if condition, no? So check. But I want to find this one parameter family of common solutions. How is it coming? Through this Pfaffian. dz is equal to phi of xyz dx plus psi of xyz dy. So I need to get phi and psi. But what are these phi and psi? They are satisfying this relation xyz phi of xyz psi of xyz equal to 0 and g of the same thing equal to 0. So we need to solve. Essentially we need to solve for p and q. Now I will use information of f. P square plus q square is actually 1. F is 0 if and only p square plus q square equal to 1. I use this information in the second one. So what I get is x minus pz. Okay, x minus pz is 0. So that will give us p is equal to x by z. So we got p. Now I need to get q. So I use p square plus q square equal to 1. This is the first equation. Therefore q is equal to square root of plus or minus, you can put 1 minus p square. But p is equal to x by z. So plus or minus square root of z square minus x square by z square. Okay? So therefore, what is the Pfaffian which we need to solve and which gives you the one parameter family of common solutions? Pfaffian is dz is equal to x by z dx plus or minus z square minus x square by z. So assume z is positive. If z is negative, you repeat. Okay? So I take z dy. So these are the places where we have to be slightly careful because we are writing root z square equal to z. Okay? Root z square is mod z, not z. Okay, we have done this. That's because I spotted z there. So this is where I was stuck. I was trying this while sitting there. Z dz is equal to x dx, lovely. But the next part, z square minus x square dy, was troubling me. How do I solve this? Right? So solving this, you need to have an eye. That's it. Otherwise, this is where I will end. I can't solve. Okay, I was thinking. Then I thought, okay, let me see what else I can do. Thankfully, the book has the answer, but in a different context, in a different way. So now you will see that this is nothing but keep z and x together, keep y separate because y does not come anywhere, no? So let's do that. So plus or minus dy, I will keep here. I take everybody this side. Z dz minus x dx divided by root of z square minus x square. This is what we have. Now you see it is good because what is z square minus x square derivative or differential? 2z dz minus 2x dx. That's what you have on the top, but for the 2. Right? So, in fact, it is the differential of this one, square root of z square minus x square. 1 by 2 root z square minus x square and 2 goes there. Therefore, solution is z square minus x square is equal to, this side I get y plus a constant square. First I get this and then square. Okay, square root of z square minus x square is equal to y plus or minus y plus constant, and then remove square root, you get square. So you have got the answer. One parameter family of common solutions are there. And you see, z will have two solutions here, but we have assumed z positive in our computation, so perhaps we don't have right to take minus. So z square is equal to x square k plus or minus y whole square, x square plus k plus, this is what we have. From here z, can I take minus square root? I don't feel I have rights because I have assumed z to be positive while passing from here to here. Okay. So this is what I think. So anyway, so we can say we have found one parameter family of solutions. At least in the upper space, z positive. If z negative, you see what to do. Looks like we have found two, because plus or minus y is also there. We have to be very, very, very careful in this. Okay, so we have done this part here. Now, why the original definition is wrong and so on? Because it doesn't go to people's notice, and Snedden is not correcting. So they have written in a journal two-page thing, but he has also written in the book. So. So we will give two examples. Example 1. One equation is xp. Maybe you can also take down this. minus, or I can share this paper. X cube minus y cube minus x equal to 0. X square p plus q minus x z equal to 0. This is one example. Okay, these are examples of compatible PDE. Okay, which you can check. The condition will be satisfied. So right now don't check. These are compatible systems. Then we have an example 2, which is p square plus q square minus 1 equal to 0. P square plus q square into x minus, I will finish this, minus pz equal to 0. Okay, this is also compatible systems. Now look at z is equal to xy plus x. It solves 1a, 1b, 2a. Yeah, it solves 1a. Does it solve 1a? Just substitute and check. You have to find the partial derivatives, right? xy plus x, which is actually x into y plus 1. What is the partial derivative with respect to x? Y plus 1. Partial derivative with respect to y? X. So if you substitute in that, x into that y plus 1 minus y into x minus x, that is 0. So it actually solves 1a. Okay? And does not solve 1b. So therefore it's not true. They have something in common, but not this one. This is not in common. Second one, z is equal to x plus y by root 2, obviously, because I want something to be added up to 1. So here also same thing, solves 2a and does not solve 2b. Okay, so this has appeared in Indian Journal of Pure and Applied Mathematics. Don't think journal means it's a very difficult thing. Somewhere you need to write down so that people can see. Maybe people are not seeing his book. So we have to convey to people, otherwise people will misled. So that's how it is. So it is volume 29, issue 8, pages 835 to 836, written in the year 1998, written by S.T. Nigam, one of the greatest fluid mechanics in 70s, S.D. Nigam and Amarnath. So he is a guru of Professor Amarnath, PhD, not official advisor, but he worked with him. He was in IIT Madras. Okay, so we will take a break for 10 minutes for tea, and then we meet after tea break. I will send this paper to you. It just has this information. Okay, so yeah. So we'll meet in 10 minutes.
Recording in progress.
So welcome back to the last session on this topic. So we will be discussing the Lagrange chart-bit method for finding complete integrals for the first order PDE f of x by u, ux, uy. So the idea is as follows. So idea is find another equation, find a g which is x, y, u, ux, uy equal to 0, which is compatible such that f and g are compatible. So the method is about arriving at this g, okay? So find this g. Okay, what will happen once you find this g? You will have a one parameter family of solutions, common solutions. So there exists one parameter family of common solutions to f equal to 0 and g equal to 0. We are not interested in any solution to g equal to 0. We are interested in solutions of f equal to 0. So we have one parameter family of solutions to f equal to 0. But we wanted a complete integral. Complete integral is a two parameter family of solutions. So we need to get that extra parameter somehow. The idea is simply this, that consider somebody who depends on a parameter. So that means it's not just one g, but there are infinitely many g's. That we have to find, so that this f and g are compatible. Then you will get a one parameter family of common solutions, but solutions of g already have a parameter a sitting inside. Therefore, that will give us a two parameter family of solutions. So the one parameter is already the a which is sitting in g, and the other one, because we are solving a equation like this, right? Phi of x, y, z. This already had the a in it, so dx plus psi of x, y, z a dy. So whenever you solve a Pfaffian, you get a parameter, let's say b. So we have two parameters. So that means we have two parameter family of solutions to f equal to 0. So this is the idea. This is a program. How to implement this we will see. So it all hinges on finding such a g's, which depends on a. Once you're done, there is nothing left, right? So it's about finding this. Of course, there is a guide how to find that g. It says I need compatibility. Let's see how it happens. So I'm following for this lecture the article of Delgado. I may be removing a certain x0, y0, z0, these kind of technicalities, but most of them will be there. Okay. So the first line here is we will look for a complete integral for f equal to 0. So f of x, y. On purpose I write sometimes ZPQ, sometimes I write u, ux, uy. So you should get used to this. Let's call this equation 1. So we will look for a complete integral for this. The usual thing is phi of x, y, z, a, b equal to 0. No, but we will look for a specific form. So look for a complete integral of the form phi of x, y, z, a, b in this form. Psi of x, y, z, a minus. So I have decided I am going to look in this form. Okay. So for each fixed b, what happens? Phi equal to 0 for now if psi equal to b. So this represents a one parameter family of solutions. What is the parameter? A. See, I want to find, I have not found. I want to find, so that will give me some conditions, how it should look like, and then we will say, indeed we have. That's a procedure, right? Represents a one parameter family of solutions, of surfaces whose normal, etc. Okay, family of surfaces. So what will be the normal? Normal to any surface which is given like phi of something equal to 0 is a gradient. So this is a geometric thing we should know. So that is dou psi. So this is a normal direction. Dou psi by dou x, dou psi by dou y, dou psi by dou. This is the direction. And this is nothing but minus dou psi by dou z of pq minus 1. So this is also a normal pq minus 1, ux uy minus 1, because I am looking for surface now z equal to uxy. So I think to compensate, this minus dou z has come. So this means the Pfaffian small p of x, y, z, a dx plus q of so this Pfaffian is integrable. I want to find a phi which looks like psi minus some constant, and I have some normal, I have pq minus 1. Okay, that means something is integrable. Okay, this is what it is. So pq minus 1 is the normal direction, because dx dy dz is the tangential direction. Okay, is integrable. Therefore, we seek functions p and q. I think earlier we wrote phi and psi in the previous lecture. We seek these functions p, x, y, z, a and q, x, y, z, a, such that what? That satisfy the equation, the just algebraic equation, there is no PD here. This we discussed short while earlier. We want to solve for P and Q, right? So it should be a solution to this. And that permits us to build an integral Pfaffian equation. So we need this such that the Pfaffian which we wrote above is integrable. If you remember, this is precisely the condition 2 and 3 in the definition of compatible systems. Of course, there was a G there, but interest was to get P and Q. Such that PQ minus 1, if you put, the corresponding Pfaffian is integrable. So that we will do in the next theorem. So it's called theorem 3, I use exactly theorem 3. Here what they do is now now I have to choose between writing and not writing. I'll see how much I write, depending on that I will decide. Not much is there, so I will write. Okay? So it will be obvious from what I am writing what could be there inside. Let x, y, z naught, x naught, y naught belong to some set U. P naught, Q naught, very obvious suggestive notation, belongs to V. And a number A naught belongs to lambda, I don't know what he's putting, tilde, which is a subset of R. Don't bother with notation, okay? You can safely ignore this because you will understand once I write what is that I want to write. Such that, so all the guys who are here are open sets, all are open sets. Such that, let these points and all be such that my f, this solves f of x naught, y naught, z naught, p naught, q naught. In other words, you see, I am getting a solution of my f. Okay, here the f is the capital F. The equation is capital F here. So let us use capital F. The PDE that we plan to solve is not small f but capital F. That's a difference. I'll stick to this instead of shifting from once in a while. Okay? So some people call this algebraic equation, but we should not call because algebraic is not like because those are polynomials. So these are transcendental equations, but let's call nonlinear equations. So f of x, y, z, p, q equal to 0. I have found p and q as function of x, y, z. That's what we have written. But what we are saying before that is that there is somebody, a solution to this. F of x naught, y naught, z naught, p naught, q naught is 0 at some point. What is the point? X naught, y naught, z naught, p naught, q naught. And so it solves that equation. Nothing, no PDE. Because for us, x, y, z is something, p and q is where gradients sit, they are written separately. So in other words, you can now write what could be the domain of f. F will be, first thing is u, next thing is v, next thing is lambda tilde. Hey, my f does not have a naught, no? Why am I writing this? F does not have. So it's a mistake. It's not there. It will come for the next one. So there is no lambda. So f is a function from u cross v to r. So we see this kind of writing when we study implicit function theorems and so on. This U is one set, but that is 3 tuples. It will consider, it's a subset in R3, and V is a subset of R2. So this is the thing. F of x naught, y naught, z naught, p naught, q naught is 0. Such a point I am taking. See, if f doesn't have such solution, even one point, then what are you talking? You wanted to solve a PDE, no? PDE means what? You want to find a function, so that when you evaluate at some points, you push it back, f of that should be 0. So if you take your function f to be never 0, like p square plus q square plus 1, you are not going to talk about its solution. Doesn't make sense. So this is okay. This is 1. Of course, lambda tilde I have introduced but not used. It will come now. Let g be a guy who is a function from u cross v cross lambda tilde to r. So g, we remember we discussed, no? We want to find a compatible family of equations with f equal to 0. That is why the g I am thinking, I am going to think of PDE, first order PDE, g of x, y, z, p, q, a equal to 0. So I want a parameter to be involved in that. So therefore, that is the reason why g has this lambda tilde in its domain. To r be a C2 function, you will see that we would need smoothness in these kind of things. Don't bother at the moment C2, C1. If you see two derivatives, you assume that that should make sense, and the order in which you differentiate should not make a difference. So that means C2. So put it like that. So G is a function of u cross V cross lambda tilde to R. Now assume that, see, all the assumptions that are really required for compatibility will come here. Assume that there is a point, it's denoted P naught because later on it will be used. That point is nothing but X naught, Y naught, Z naught, P naught, Q naught. I'm happy with this first 5 tuple, no? Because F is 0 there. Now I have for G extra variable. So I will add one A0. So in fact I'm saying there is this P naught is actually I'm saying there is a naught such that this happens. G at P naught is 0. Should be. It's not written, it should be. But not this. I want to know, I have a point at which F is 0, X naught, Y naught, Z naught, P naught, Q naught. G is 0 at a different point, there is a A0 there. So you can think first one also has a A perhaps which is not appearing. It's constant in A. But important thing is this, such that this condition, this Jacobian, because Jacobian non-zero is what will guarantee you can solve things. P naught not equal to 0. See, actually it does not make sense to ask this, because what do you mean by derivative of F with respect to Q at P naught? P naught is a 6 tuple, whereas my F is defined only on 5 tuples. So you can assume it is defined, but it does not depend on that. With that understanding, this is fine. Okay? So I have F equal to 0, G equal to 0 at this 6 tuple, X naught, Y naught, Z naught, P naught, Q naught, A naught. And I know the Jacobian with respect to PQ is not 0. Therefore, implicit function theorem tells me, I will write for once the conclusion of implicit function theorem. Okay? So can I think, this is like this. I can think, no? It's a matter of adjusting, exchanging some. Because I feel better with this, that's all. You need not do this, I'm just saying this. You can ignore this. Theorem is true, there's no problem. It will help me in writing, that's the reason. We have assumed at this point, both F is 0, G is 0. That means a common solution. This point P0 is such that F of P0 and G of P0 are 0. And the Jacobian is not 0 at P0. Therefore, implicit function theorem tells us what? PQ can be solved in terms of the rest of the people. Okay? PQ, this is how we should remember. We should not remember there exist neighborhoods, etc. That we can naturally write. There are certain things that will naturally come, but the idea is important. Oh, PQ can be solved. What it means, we know what it is. So PQ can be solved in terms of the whoever is rest. In terms of who are the other guys remaining? X, Y, Z, A. These are the variables remaining. So that means what? There exists a neighborhood or open set containing where? Near this P naught only. Whoever is acting in P naught, only those points. Containing which point? X naught, Y naught, Z naught, A naught. Right? Other one is not important. And a neighborhood of where it takes the values P0, Q0. And a function. Function from where? This neighborhood, I don't know what I should call, I have already used omega 1, no. O, open set, O1, O2. O1 is an open set around these 4 things. O2 is another set, not oxygen. There is a function from O1 to O2. Function, if you want, you can give a name. We are using all the names actually. I use a crazy function, eta, from O1 to O2. Now it's clear what is that we want to say. So anybody here, it looks like X, Y, Z, A. That guy will go to eta of X, Y, Z A. Remember, O2 is a subset of R2. So it will look like two components, eta 1 and eta 2. So this is actually, in terms of the component functions, eta of x, y, z A, eta 2 of x, y, z A. Right? Any function which takes values in R2 looks like two functions. One function in the first coordinate and another function in the second coordinate. So this is how it looks. So I have, in fact, instead of saying there is a function eta, some people may say there exists functions eta 1 and eta 2. So this is a function, but what is the property? Property is this: f of x, y, z, eta 1 of x, y, z, a, eta 2 of x, y, z, a equal to 0, and it solves those two equations, f equal to 0 and g equal to 0. Okay? So in other words, we can say I have solved p in terms of the rest of the variables, q in terms of the rest of the variables. Because I have used a g featuring a, I now have a one parameter family of one parameter family actually here, right? Because it depends on a also. Is it clear, this part? So this is just by implicit function theorem. So this we actually proved. This is one of the conclusions. The second conclusion is what we have seen in the morning in the definition of compatibility. So this is one which we have actually proved now. And the second part, he has given a wonderful name to that. That O1. O1 he calls delta. Okay? And delta also like Laplacian. So we should not use in this course. We are seeing Laplacian. So you have said you have found something earlier. Okay, fine, no problem. In O1. For each of this, what happens is the following. Dou Fg by dou Pq into Q dou P by dou Z minus P dou Q by dou Z plus dou P by dou Y minus dou Q by dou X. Yeah, in fact, this eta 1, eta 2 is precisely P and Q. P of this, Q of this. And that is the P I am talking about here. It's a long equation. Minus Fp Gx minus Fq Gy minus. These are interesting combinations. If you have studied PDE in your MSc, you will recall seeing P of P plus Q of Q kind of things. Gz plus Fx plus Pfz into Gp plus Fy plus Qfz to Gq equal to 0. So this is what it says, this new condition. Imagine from here the compatibility follows. In other words, that Pfaffian P dx plus Q dy minus dz equal to 0 is integrable. Then you have got a family of solutions, one parameter family of solutions. Because your thing already has one parameter in it, you will get two parameter solutions. So we're done. So this is that really. So why is this condition satisfied? What are the assumptions we are making in this theorem? F equal to 0, G equal to 0. You can solve for P and Q in terms of this. Now we are saying that we can actually find such a G so that the compatibility condition is satisfied. Then we are done. So we have not yet shown the compatibility condition. If we can get some compatibility condition from here, then we are done. I think that is the next theorem. So now it's a matter of computation, I think, nothing more. We will do that. See, what we have is for every x, y, z, a in our O1, we have that capital F of something is 0, capital G of something is 0, right? So that we need to keep on differentiating and get some get this relation. Actually, it is algebra. What we are going to see is differentiate and then suitably multiply, get that equation. So this equation can be got just by differentiating these two things. Okay? Suppose I want to differentiate the first equation with respect to x. How will it look? Fx plus Fp, Px or dou eta 1 by dou x, plus Fq, Qx equal to 0. Right? So let me write that. So differentiating with respect to x, that f of that equal to 0, what I get is fx. Then we remember we have to differentiate with respect to fp and then write dou p by dou x, and then fq and dou q by dou x equal to 0. Same thing you will do for g. Same thing will come, right? Because everything is same but for the name f and g. So for g you will get gx plus gp dou p by dou x, gq dou p by dou x. Now differentiate with respect to y. Okay. Now from here we can get some expression, these two. I will just do this and I'll say rest is same. From here we get an expression for this fx gp minus fp gx minus dou fg by dou p cubed into dou q by dou x equal to 0. This implies this. Okay? And then differentiate with respect to y and do something, you get something. Then differentiate with respect to z and you will get something. Right? We can differentiate with respect to x, y, z. We can do that. With a also we can do, but we are not doing. Not doing. At the end we will have, so with respect to x gives you one equation, with respect to y gives you another equation, and with respect to z, when we do we get actually two equations somehow. Please see what is written here. Then it's a matter of multiplying suitably and adding up, you will get this equation. It looks quite complicated, no? Where is this? This one. So you will get this expression. Okay? Actually in this, do we see any, that compatibility thing is not seen, no? In that form it's not written. Okay, fine. So this we have proved. So this looks like there is no integrability involved so far. Okay, this theorem is only about applying implicit function theorem and solving P and Q in terms of this. Because we already assumed there is a G. We have not yet found the G. We assume there is a G such that a G of x naught, y naught, z naught, p naught, q naught, a naught equal to 0. And f anyway is 0. And then we assume the Jacobian condition. So that I got solutions for P and Q as functions of x, y, z, a. After that we just use this relation, differentiated, and then we got whatever condition is given there. So this is pretty general, right? We have not yet found that G. Now we need to find that G with some conditions so that it is compatible. Then only we have finished our job. So that is the next part. Is it clear what we did so far? We have not got any G which is compatible. We just assumed there is a G such that I can solve for P and Q as common solutions because that's what in my mind to come later. And then I saw what is the equation I will get, some relation what I will get. Why should I be interested? It's not clear unless we apply this in the next theorem. So this must be some, proof must be going very, very long. Then they thought let us keep things separate. This is nothing to do with my PDE, so in some sense, right? Not about any solution. So take it out and keep it separate, so that we can follow in pieces very cleanly. That's why we see a lot of some crazy technicalities as lemmas. Because that's not main idea. Main idea we already explained. Now that's what is going to come now in this theorem. So, theorem 4. This is I think the final theorem. Now let G, now this is where he is asking, G, U, we already knew what it is, right? That function B, C2 solution, don't look at the moment the C2 solution of the linear PDE. Linear PDE, okay? I have a feeling this is quasi-linear PDE. You know the difference between linear and quasi-linear, right? Maybe it's linear. Let's see. Yeah, you see this is the equation for G. So equation is this: Fp Gx Fq Gy plus Pfp plus G QFQ. This looks like that which I wrote in the second line in the previous theorem. QFQ. Okay, got it. Into Gz minus Fx plus P Fz Gp minus Fy plus Q Fz Gq equal to 0, okay, which verifies some hypothesis. That is the one in the previous theorem. See, the f coming here is the f which is given to us, the PD that we want to solve. The complete integral that we want to find for is a capital F equal to 0, which verifies the hypothesis 5, that 5 is the that there is a point at which this Jacobian is non-zero. Okay, that hypothesis is precisely this. That is the hypothesis. Because we want to be able to solve, right, for P and Q in terms of the rest of them. That's it. Now suppose this is the case, okay, suppose I have found a G with this property, then what do I have here? What does this equation stand for? So whatever I am writing, underlining with this red part is gone, right? And what I have is dou F is dou PQ into something in that square brackets is 0. But dou FG by dou PQ is not 0 at that point P naught. Therefore, by keeping in a small neighborhood around that, it will continue to be non-zero. So we can cancel that. So what remains is the one in the square brackets is 0. Q dou P by dou Z minus P dou Q by dou Z plus dou P by dou Y minus dou Q by dou X equals 0. That is precisely the integrability condition for P dx plus Q dy minus dz equal to 0. So P dx plus Q dy, remember this is the thing that we wanted to propose, no? For the vacuum, equal to 0 is integrable. In fact, we computed this in the last lecture, x dot curl x. If and only if this bracket is 0. And then we are done. So all remains for us to do is solve this particular linear equation. Linear or quasi-linear? Linear, no? Because what are the coefficients? Let us look. You know the difference between linear and quasi-linear, no? Quasi-linear, at least in two independent variables we saw, is A xyz ux, B xyz uy is equal to C xyu. That means what is unknown here? There in that example, u. Here the unknown is g. Does g appear in the coefficients? No. What appears is f, g and so on. Right? No, f, p, f, p, q, f, q, etc. They all depend x, y, z. Z is there. I don't understand. There is z. Yeah, x, y, z is there. G itself is not there. Z can be there. G itself is not there. So this is actually PD in how many variables? That's the important thing to note. I got the confusion earlier, what is this? No. This is a PD in how many variables? What is that we want to find? A function of how many variables? X, Y, Z, P, Q and a also, right? The equation is in x, y, z, p, q. That means so many variables. So this is a linear equation in 5 variables. So no problem. Huh? This is linear. Coefficients are allowed to depend on x, y, z, p, q. It should not depend on g. So this is linear, is correct. I saw some book writing quasi-linear. That's why I was worried. I think Amarnath writes quasi-linear. Please check that. It is linear. Delgado is correct. Linear. Okay, fine. And then what is the conclusion? Now we see he has to still write some conclusion, so he will write. Let. So assumption is G is a C2 solution of the linear PDE. First assumption. Second assumption, let P comma Q be functions whose existence we call eta 1, eta 2 in the proof, whose existence was proved in theorem 3. Because I am going to introduce that Pfaffian here using those P. That's why I have to introduce who is P and Q. P and Q are the functions whose existence was proved in theorem 3. Huh? Okay, so that's the assumption. Then the Pfaffian P of x, y, z, a dx is Q of x, y, z, a dy minus dz equal to 0 is integrable. Okay? We have seen that, no? We just observed that if G satisfies this PDE, the previous theorem 3 had an equation, and because the Jacobian is non-zero, that square bracket thing is 0, which is a solubility condition for this Pfaffian. This Pfaffian is soluble if and only if that condition is satisfied. So we have proved this theorem. Okay? Now the question is, how do you find such a G? It all reduces to finding a G, we featuring a parameter and solving this equation, this linear equation. How to find G? Very easy. Okay? How do you solve AUX plus BUY equal to 0, C? And these are functions of x and y. All are functions of x. So that is simply this dx by axy. This is correct, no? You have to solve these equations. dz, that's what they write. Cxy. Okay? Now you have n number of variables, you write n number of them, that's it. So if you notice here, they have carefully written Cxy, u can be there here, no? Linear I want. These are the non-homogeneous equation. Yeah, it can be Cxy, u, in fact, it can be there. That's a linear. We are in a special linear situation. So exactly that, you want to solve this equation, it should be, I will write the equation here itself. dx by fp equal to dy by fq equal to dz by pfp plus qfq equal to dp by whatever is here with the minus sign, minus fx plus pfz, and last equation I write here, this is not equal to this, so maybe I'll write this. And the last equation is dq by whoever is here, minus fy plus fz. These are the famous Chapman's equation that every PDE book writes. Okay? In fact, using characteristic method also you can get these results using geometrical things, right? So I have derived these conditions in the NPTEL lecture notes, NPTEL lectures whose link you have got. You can see there also. How to solve nonlinear PDE, how do we take motivation from quasi-linear PDE. Quasi-linear PDE, several things are very easy, the geometry is very simple. Whereas nonlinearity is not clear because it just mixes all the things inside. See, ux, uy minus 1 is a normal to a tangent plane. And your PDE is AUX plus BUY equal to CXU. Therefore, you can know the answers. But if it is f of xy, ux, uy equal to 0, it's not very clear who is your ux and uy is from this. You can't. So the geometry is slightly complicated, but that's where this Monge cone or whatever such things come. Or you can also, people also work with this Charpit's equation. Same equation, if you want to solve the equation, no, f of something equal to 0, finally same players are coming in. This is another way of deriving, that's another way of deriving. Yeah, there is a type in Delgado, equation 14, he writes a dp once again, very obvious, you can see, both are dp, one is dq. Okay, so now algorithm is very clear for us if you want to solve. If you want to get a complete integral of a nonlinear equation, you would find that g, you have to get the Pfaffian, solve the Pfaffian. Finding g, you have to solve this linear PDE, which is easy, you can solve. I will not say it's easy, but this is what you have to do. After getting this, from here you have to get your P and Q, get the Pfaffian, solve it, then you will get two-parameter family. Okay? So I think I am not able to do this Jacobi because there is no time at all. But you can now see what they will do. Let's explore idea-wise. Jacobi method. First of all, this is for not one variable, two independent variables, but three independent variables. I don't know what the notation you have put, but because sometimes we call z equal to uxy, that's why we call z. But now there is no z, we are in 4 dimensions. We know only up to 3 dimensions x, xy, xyz. If you have 4 dimension, maybe w, but we don't know, nothing is standard. So that's why the problem is using z. No? So it's a 3 independent variables. What should we do? What should be a complete integral? We had some kind of discussion right yesterday. It should be a 3-parameter family we want, right? So looking for a 3-parameter family of solutions. That would be the complete integral. Done. How will I get 3? I don't even have 1 here. So the idea is, you have f now, come with your g1 with one parameter a, okay, another g2 with another parameter b, okay. Now some kind of compatibility etc. will be there going on, some new Pfaffian will be formed, so there will be a Pfaffian. Now you solve for your PQ, and you see again the problem R. The standard books are written for 2 variables. Therefore, when they write R, it will mean second order derivative. We wrote this yesterday. But here we are putting this notation, so you put. So solve for PQR using this f, G1 and G2 equal to 0. Exactly how we described in the beginning of this lecture. Okay, so if you want, put implicit function theorem assumptions and so on. So you will get PQR are solved. Now you propose a Pfaffian which should be P dx, Q dy, R dz equal to d something else, right? W. This Pfaffian should be integrable. And do I have integrability condition for this Pfaffian? We have studied only Pfaffian in how many variables? Right, 2 variables. This is where I stop. So now look Amarnath's book. What details? This is what they are doing, I have seen. But you will just see the further finer details. So I am not solving any example because the example is there. If I am doing also, I wanted to mention one important thing, I will do that. I won't solve, but I will just indicate. This is example, so you can see. This is example from the book. 174, page 29. The f is x square, p square, x square, p square, plus y square q square minus 4 equal to 0. This is the PDE. Now that equations we wrote, for the g, that dx by something, dy by something, those are called in this book as auxiliary equations. Because your job, your interest is not to find for g, right? Your final aim is final, which is to solve this f equal to 0. So that's why they call it some side items. So auxiliary equations are dx by fx, na? fp. So what is fp here? 2px square. 2px square. So 2x square p dy by 2y square q dz by p of p plus q of q. So 2x square p square plus 2y square q square. dp by minus fx plus pfz. So that is minus 2x p square and dq by minus 2y q square. This writing this is the easiest part. Now how do I solve this? So now what he does I am showing you. So this is one approach. He is solving, I am just repeating from this because you have to spot which you can solve easily. So that cannot be explained. He spotted this. From here he is going to cancel y and a q, so he gets and also a 2. So dy by y is equal to dq by minus q, which he can integrate now. Okay, so that will give you qy equal to constant. So he calls it qy minus a equal to 0. Okay, this is what he is calling as g. Okay, now therefore q is equal to a by y. Our idea is to solve for q and p, right? And p is equal to, so our idea is really not interested in that g. What you need is finally that p and q. Right? So he used the g idea, wrote those equations, auxiliary equations. But you don't have to find the g. In fact, it is impossible to find g's. You will realize when you are solving first order PDEs. So here interest is only q and p. So q you have got, and from your equation you solve for p. Your equation is x square p square plus y square q square minus 4 equal to 0. From there you get p is equal to root 4 minus a square by x. So that will give you the equation dz is equal to square root of 4 minus a square by x dx plus a by y dy. See, he has inserted the parameter a here. You have got p and q. Now you solve this. That is very easy to solve here. So z is equal to square root of 4 minus a square log x plus a log y plus b. So you have got a complete integral. But so here remember what the combination is y and q combination we considered. But you can also consider some other combinations. So he himself is writing dx by 2x squared p is equal to dp by x and p combination minus 2xp square. If you use this combination, you will end up with z is equal to a log x plus square root of 4 minus a square log y plus b. So he has got another complete integral for f equal to 0. Both are complete integrals. Okay? But if you look from long shot, both look same. B is outside, root 4 minus a square sometimes hanging with log x, sometimes with log y, a log y. But if you see equation itself is quite symmetric in x and y. X square p square, y square q square. So therefore he says, there is a comment on this, that's why I wanted to do this. He says these are two complete integrals are equivalent, he says. So we have to understand what the meaning of this is. Okay? A first order PDE can have several complete integrals, he has declared in the note. But these we understand that they look alike or something. For that reason, he says these are equivalent. That means you can obtain one from the other merely by a change of choice of arbitrary constants. That's what he explains. Now he gives another example where and exhibits. So this is the next example. 175. PDE is z square into 1 plus p square plus q square equal to 1. Now he gives two complete integrals. I think this equation is familiar. We derived this equation. And y minus mx minus c whole square is equal to 1 plus m square. There are two parameters here as well, but both are complete integrals. But they are not equivalent. Okay? And now we had the auxiliary equations. I think we took only an example. It was easy, we could solve. Now you ask questions, hey, for what kind of things are easy, there are some standard types. When your equation depends only on p and q, life is simple. If it depends on only on z, p and q, not on xy, it's again simple. And if it looks like gxp equal to hyq, xp things are separated, yq things are separated, that's also simple. So these are various special cases where you can do quickly. Finally, you have to solve the same set of equations. But for these kind of classes, you can give much simpler expression, and this is what people, the coaching centers make people to remember this. बच्चों ये देखा तो यही आएगा, ये याद रखना. It has gone up to the extent that even wave equation, we have on bounded domains we solve with Fourier things. अगर यहाँ पे ux का condition दिया है तो यही आएगा, u दिया तो ये आएगा. So if you want to set some question, you can't set question because it's making memorize all the things. But the problem is if you keep on changing these conditions at your will and wish, solutions will not be, nice solutions. They will have problems at the endpoints, at the boundaries. Therefore, that will go outside the realm of the regular classical PDEs. So that I think that's the reason why they keep on inserting this discontinuous data and make you solve, so that you don't say it's out of syllabus. But proper thing, mathematically, that is not correct. You need some justification of generalized notions of solutions. Okay, so I will end here. I will send you this paper by Professor Amarnath and Nigam, and I have sent the Delgado. Please read, very simple. It's actually, I have seen, it's a classroom notes, meant to very clear, very solid. I don't think anything can be clearer than this. Particularly, he has written the application of, instead of hand waving, very clear neighborhoods, etc. Not a big deal. Once you understand, you can also write. But if you write like this, people are driven away from this material. Maybe that's the reason why others don't choose to write these things. Thank you. Any questions you have, you can send me an email.